Hello world, here's Jorge and let's continue learning about object detection in PyTorch. In the last video, we ended by talking about pooling layers, and now I want to show you how we simply can, say, adapt the code that we explained in the last session in the actual HOG net, in the actual class, right? So first of all, we defined the directional projection filter. So we essentially defined the weights, the hard-coded weights, and then we replaced the PyTorch weights with our own, yeah? And we did the same with the bilinear spatial binding, yeah? And with essentially with our pool layers. But now let's actually continue. Let's actually continue with our, say, construction of the HOG net, and we're going to continue by talking about the block pool. Okay, so let's do that. 3.7 block pool and padding. Pool, right. Great. So what do we mean by block pool? Yeah. Let's see. So essentially, let's write this down. So the purpose of block pool is to sum over the gradient contributions across all orientations within a given block, producing a single scalar value per given block. So essentially, this is doing actually something that is a bit similar to our pool layers that we have defined above, but with one key difference, one key distinction, and that is the following: that this layer doesn't distinguish between positive and negative directions. Okay, this is unlike the block pool, unlike the pool U and pool V layers, which indeed compute the features basically based on the orientation. So they are orientation specific in the sense that, remember, we needed to take both positive and negative directions into account. That is why we, for instance, here above, we had to multiply by 2 because we were taking into account also the negative directions. Here in the block pool, we are not going to do that. All right? And well, so you might be wondering, what is the advantage, right? Why not just using again the or not introducing at all this block pool? So there's an advantage, of course, and that advantage is that this layer is going to mainly focus on the main characteristics or the strength of the gradients, okay, rather than their polarities. Okay, that is the main say advantage. Okay, so we can write that down. So the advantage of block pool is that it's going to focus on the strength of the gradients. Okay, so that is going to be the main focus of this layer. All right, but yeah, let's code it out. So let's start by importing torch and torch.nm. All right, so let's for now let's stick to number of rotations is equal to 9. You'll see that later on I will set it to something different, something simpler. Okay, but for now we are going to stick to it. Yeah, so number of rotations equals 9, and then let's define this block pull. All right, and how are we going to define it? So of course we're going to use once again a convolution layer. Okay, the convolution layer comes to D, because at the end of the day what we're doing is essentially the same that pull is doing, but in this case we are not taking into account the say positive or negative orientations. We say take an overall estimate. Okay, so come to D, and well, the input is going to be number of orientations instead of 2 times number of orientations. The output is just going to be 1. It's going to be 1 channel, and the kernel is going to be 2 by 2. And again, we're going to set the bias to be false. Okay, which is just very similar reasoning as we've been applying for instance, our pool layers. All right, but remember, once we define the layer, so here we define the block pool layer. Okay, so once we have defined that, we need to replace the PyTorch weights with the actual weights that we essentially want to say hard code, right? We could call it like that. All right, but yeah, remember that before doing that, what we needed to do is to check the shape, right? And by the way, we are going to replace the PyTorch weights with ones, okay? And I will explain that also. I will explain why we're doing so after we check the, say, shape of both weight, PyTorch weight, and essentially the hard-coded ones, okay? So let's continue now. And what we need to do is, of course, as always, extract the weights, the PyTorch weights. All right, so let's do that. So block pull dot weight data, and that is going to give us the PyTorch weights. And yeah, just to have a look, let's print it up. You see, there we go. There is all the PyTorch weights for us. And just to visualize better, let's see the shape. How does it look? Okay, great. So we have one batch 922, right? We have essentially, well, not batch. What I mean is, this is the output channel, this is the input channel, and the kernel size, right? As always, great. But now, what do we want to do? What we want to do is to essentially create a PyTorch tensor of ones, right? So we want to do it with that exact same shape. So actually, let me print this so that we can compare it later. Great. So now let's do that. So how do we do that? So torch.ones is going to create a PyTorch tensors just made of ones. And well, how do we shape this? Well, we just want the same shape that we got with the PyTorch weight. So essentially that is one output channel. Number of channels, well, so it's 9. Okay, so of course number of orientations. and again, kernel height, kernel weight, right? So this is going to give us the shape that we want, right? So so that we can verify, let's actually shape this. Exactly, correct. That's what we want. And as the shape of both is the same, we can directly, essentially, replace. So replace PyTorch weights with ones. Okay, we'll see that. We'll see why we're doing that. We're doing that later. Okay, so essentially, we simply take this without the shape, of course, and equalize it to the torch.ones. Great. There we have it. That's fantastic. So we just do that. Great. Okay, so now how can we proceed? Well, first of all, let me explain why I replaced, say, the PyTorch weights by ones. So the reason why we're doing that is the following. So the reason we replace the weights of block pool with a tensor of ones is that the block pool layer, well, let me actually mark down this, and of course this is to be highlighted. Great. So that layer is that So is that the block pool layer is not intended. So we are not aiming to learn any new features, okay, with this specific layer, but instead we simply want to essentially add things up. So essentially aggregate information, okay? That's all we want to do with this layer. We don't want to learn any new features. That's why we just set it to equal to 1, so that we just apply this layer to aggregate gradient information, okay? So it's not intended to learn any new features, okay? That's why. We just aim to perform an aggregation operation. Okay, fantastic. That's great. So now we understand why we are using this layer, this block pool layer. But I also mentioned padding. Okay, a padding, say, feature here. So first of all, what exactly do I mean by padding in this context, right? So essentially, let me actually write that down. So we're going to introduce, say, class in PyTorch that adds padding for us, okay? And that is going to be called nm.replication pad, okay? And more specifically, replication pad 2D, yeah? So this is what we want to apply now. So this is going to pad the input tensor using replication of the input boundary, okay? Okay, so there's no better way than actually see it in action. So let's introduce a tensor padding, and let's call it m, for example. Let's store it in the variable m, and just we're going to say
So replication
replication 2D. And to begin with, let's just set it equal to 1. What is this variable doing? Well, it's actually telling us, initialize internal module state shared by both. Oh, no, it's not that. So essentially, what these parameters are doing is the following. So is the size of the padding. So essentially, is going to add as many, say, rows or columns or both that you import in the class replication pad. Okay, but yeah, let's see how it works. Let's just start with adding 1, yeah, and see how that works. So let's just say random tensor, and let's just define, yeah, just a range, right? So torch dot range, because remember that in PyTorch a range is with a range, and just say, for example, a range of 4, right? What is this going to give us? Well, let's visualize. Random tensor, let's see. Okay, exactly. So we got a 1D tensor with 4 elements, 0, 1, 2, 3. And the question is now, if we apply this random tensor as it is right now, do you think it's going to work? Do you think it's going to give us, say, it's going to essentially path for us? Let's see. But first of all, let me print this for reference later. Okay, and so essentially we're going to have these random tensor that needs to be applied to the replication pad class, right? So how do we do that? Essentially, what we can do is just having as an input. Okay, so we can do random tensor and see if it works. Let's see. Oh, it didn't work. It says padding length should be less than or equal to 2 times the input dimension. Okay, but got as an input 1 dimension, and the padding length is 4. So essentially, it's telling us, look, if you don't give me an input that is 2 times the actual input dimension, okay, it's not going to work. Okay. All right. So this means that we need to change the dimension. All right, we need to change the dimension, and it needs to be in this case 4D. Yeah, because it's 2 times the input. So, and actually, if we go to the documentation, you see, actually, here is more clear. The input needs to be 4D. Okay, needs to be 4D. So this is not going to work as it is right now. So how did we say change the dimension from being 1 to 4D? We have done this in the past, and there's doing this applying reshape. Okay, so if we apply reshape, we're gonna achieve just that. And now the question is, okay, should we say place our information, right, the 4 elements in our 1D tensor, should we place them in the columns or should we place them in the rows? And that's a good question. And it depends, the answer is it depends on where you want to pad. Okay, and let's see that in action. So let's say that we want to store the information in the columns, right? So how do we do that? Well, first of all, we need to reshape it to a 4D. So 1, 1, 1, and we want to store the information in the columns. So it will be -1 here. All right, so what's going to happen if we just run this? Great, at least it worked. And see what happened. See what happened, that we got padding. We got padding in the columns. All right, we got padding in the columns because you can see how now we got 1 extra column at the beginning and 1 extra column at the end. All right, so we just got that, say extra, say padding. We got that padding in the in both columns. All right, but let's explore. And what happens if we were to, instead of store the original information in the columns, we were to store it in the rows? Let's see. Okay, so now instead of having, well, first of all, the shape changed, right? Now we got a 4D vector that has four essentially elements here, but essentially what we observe is that now we need to look at the columns and see, because now essentially we got 0, 1, 2, 3, because remember we are having a range of 4, so 0, 1, 2, 3, and we got essentially padding at the rows. Okay, so we got, and actually I think the best is to compare both. So actually let's compare both and print them. Okay, so what we need to do is just to do this twice, and let's compare. Oh, what happened here? Let's see. Oh, of course, this is not print. Okay, so print like that and like that. Great. So, and of course, let's change this. Okay, so what we can see now, and actually for better reference, let's also print the torch.arrange. Okay, just for reference, the original one. Let's just space here. Fantastic. So you see, we started with a 1D essentially tensor here, and what we then did was to expand. Well, not to expand, to reshape, to fit to a 4D. Okay, and just let's look at the structure 0, 1, 2, 3. Okay, so essentially what happened is here 0, 1, 2, 3. This is the original, right? The original, say, tensor, yeah. And what we did was to essentially pad it. We padded it, and actually, because right now, let's actually the best that we could do is to also visualize the shape. Okay, the shape of it. So that is more clear. Okay, great. And same. Fantastic. So you see the difference. The main difference after padding. Well, let's also this print is. Great. So you see, this is the main difference. That if we place. So we store originally the information in the columns, and then we apply the replication pad. Essentially, we're going to get 3 rows and 6 columns. All right, we're just going to get that. And if it's the other way around, or the essentially the information, so the columns are going to be 3 and the rows 6. So essentially what's happening here is that if we choose to store initially the information in the columns and then we apply replication pad, we are going to get essentially padding in the columns. Okay, we're going to get this padding in the columns, while if we apply it to the rows, yeah, so if we store original information in the rows, we're gonna get the padding in the well, in the rows in this case, while here it was in the columns, because we had essentially added one extra column here of zeros and one extra column of threes, while here we got one extra row of zeros here, and we got one extra row of essentially of threes here. But yeah, essentially that's what we're doing here. We are padding. The main message is that with replication pad we can add rows and columns of our original information. But yeah, you can of course play more with this replication pad 2D class. Great. But essentially to our original code, so to this class, what we're gonna add at the end, well, what we're gonna incorporate is just this line. So we're gonna say padding is going to be equal to this nn dot replication pad 2D, and we're gonna say just one, so just one row, one column. Okay, and you'll see that we'll use that later in the HOGnet. Okay, so this is creating padding for later in HOGnet. Great, but yeah, that is clear now. And now let's essentially move on and start with the definition of glyphs. Okay, so let's do that. So 3.8 glyphs for rendering the HOG extractor. Okay, great. So what we're gonna do is to introduce so-called glyphs. Okay, but what are glyphs, right? Let's see. So glyphs are small patterns. Okay, are small patterns. Actually, small, you could call small visual patterns that represent the gradient orientations. Okay, and again, I stress that since we already introduced the block pool, we're going to just be talking about the 9 base orientations. Okay, not 2 times that 9 or 2 times the number of original orientations, just the original orientations. Okay, great. So actually, there's no better way of understanding how these glyphs work than just going through it, just actually coding it and see how it goes, see how it works. So let's do just that. Okay, so to start with, let's just import numpy as np. And okay, now remember when I said that I would change the number of orientations just for now, just for the sake of clarity and explanation, like it got so that it goes smoother. Okay, so the time has come. Okay, I'm gonna change the number of orientations, and I'm gonna change it to 1. Very simple, just one possible orientation for now. Okay, and also I'm going to introduce a variable, okay, that represents the size of the glyphs. Okay, the size of the glyph, and this GS, and just let's keep it simple. So I'm just gonna set it to equal to 3. Again, in the original code, when we finalize the HOGnet, you'll see that actually number of orientations, of course, is 9, and the GS is going to be 21. Okay, so imagine. But now we're just going to keep it simple so that we can actually understand the base, understand how it works, how the code works, and we can then generalize, right? Okay, so let's start the definition of the glyph by defining the grid points, Okay, so we're gonna need to define the grid points first of all as the starting point for our glyph definition. Okay, so let's do that. Define grid points. Great. So let's do that. So u is going to be equal to, yeah, let's just split it equally in space. So for that we just use linspace. Okay, and yeah, we're gonna make it go from -1 to 1. Okay, from -1 to 1, and with a space of course GS. All right, so of course, if we visualize that, you see indeed we get 3 elements in a 1D tensor, -1, 0, and 1, right? In a float mode, right? Great. What is next? Well, what is next is that we don't want to be working with a 1D tensor, all right? We now want to actually be working with a 2D, okay? With a 2D, and actually that 2D, then we're going to modify it accordingly. Okay, so based on the GS parameter, so the size of the glyph. So we basically are shaping our tensor so that we get the right, shape for our glyph, right? Okay, so now first of all we need to modify this, and we need to reshape it. Okay, so we're going to do just that. So linspace, this is exactly the same. Have -1, 1. Yes, and here what we want to do is to reshape this. Okay, so we're going to reshape, and to what? Well, first of all, we want to keep the rows. Okay, so we're going to keep the rows. So that's why we play the -1, and we're just going to add columns. We want to add columns to it. So this is just essentially going to make copies of the rows. Okay, let's visualize that. Exactly. Yeah. So we just get copies of the rows, and but now what we want to do is to also yeah, essentially expand this tensor. Expand this tensor so that we modify the columns now. Yeah. So let's do that. So essentially what we can do is the following. So we can do u, and we can do torch. Well, I can actually get rid of this. Torch, linspace, same shape. We're going to do reshape here again. Reshape. Again, I'm writing everything down line by line so that is everything very clear. Of course, we could do all in one line, and then we expand this. Okay, and we expand it in what way? Well, we want to keep the rows. Okay, we want to keep the rows, and now the columns we're going to set it equal to GS. So essentially, what this is going to do is going to introduce GS columns. It's going to introduce GS columns, and you can actually verify this by printing it out. So indeed, we went from having a 3x1 shape to a 3x3. Exactly. So now we have a 2D tensor with say a 3x3 distribution. All right. Great. Fantastic. So now we need to specify what is this U, right? So this U is actually the elements of a point. So what do I mean by that? So in a grid, in a 2D grid, right? So what we're going to do is, what we want to do is define to the grid, so to the grid points. This is the goal now. And we start by defining horizontal or x points, okay, so x points of the grid. So define x to the grid points. Okay, so of course in a 2D grid we're going to have x elements and we're going to have y elements. So the x elements of our points are given by you. Okay, are given by you. So these elements represent the x, all the x values of our grid points. Okay, great. So what are we missing? Of course, we're missing the essential. Actually, let me print it out because it will be good for comparison. So print great. So essentially now we need to define the y. So define y to the grid points. Okay, so we now are going to do the analogous with the y. And how do we do that? Well, we essentially take the transpose of the u. If we just take the transpose of the u, we're going to get the, say, corresponding y values to the given x values. All right? So let's just take the transpose. We just take the transpose. All right. And yes, let's have a look. Well, of course, you need to print it out. Great. So essentially, let's have a look. So what information is are these two tensors storing? So essentially, the following. So this is the x is equal to -1 and y is equal to -1. Okay. So essentially, if we go here to the diagram, okay, the -1, -1. So -1, -1. So is this point. Okay. This is the point that these two elements are representing. All right. So how about the others? So essentially it works the same way. So -1, x is equal to -1, y is equal to 0, and x is equal to -1 and y is equal to 1, and so on. You see? So you can see that we have a collection of points. Okay, we have a collection of points, and more specifically, we have 9 points. All right. So all the points that I have drawn here, okay, all these 9 points are stored in these two tensors. Okay, so u and v do exactly that. All right. Perfect. So let's just print this out for later reference if you need it. Okay. Great. So what is next? Well, now something that is going to be useful is to store what is the distance of all the points with respect to the center. Okay, with respect to the reference point 0, 0. Okay, so to do that, we just take the Euclidean distance. Okay, that, remember from math, is just the square root of the say x value of the point squared plus the y value of the point squared too. Okay, but let's just call that out. So here we're gonna do the following. So store distance from all, so store all the distances of points from the reference 0, 0. Okay, so let's call that out. And let's start with n here, and this is just going to be, of course, torch dot square root, and we're going to have u squared plus b squared, and Great. So let's visualize this. Let's visualize this. Fantastic. So let's actually see if this makes sense. Let's see if this makes sense. Look, let's start with this distance, for example, 1. This 1 is the distance of what point with respect to the 0, 0. Well, let's look at the same position of the other two tensors. So -1, 0. Okay, so x is equal to -1. So x is equal to -1, and y is equal to 0. So we're in this point, and essentially we are looking at the following arrow. Okay, we're looking at this distance right here. Okay, we're looking at this distance right here, and of course this is just going to be 1. Okay, it's just going to be 1 because it's equally spaced, and it makes sense that is 1. Okay, the distance between these 2 points, because of course is the point 0 and 1, right? Sorry, the -1, 0. So x is equal to -1, y is equal to 0. So the distance is going to be 1. Okay, great. But what about, for instance, this value that looks a bit different? So this is, of course, the distance between the point -1, -1. So essentially, this point right here, -1, -1, this point right here, to the center. So what is the distance? Well, the distance, just simply applying Pythagoras. So we have 1 here, we have 1 here. So it's going to be, of course, the square root. So the square root of 1 squared plus 1 squared, yeah. And this is going to give us square root of 2, which is 1.4, and so on, yeah. So essentially, this is the distance, indeed, that we are storing in our n tensor. Indeed, is this is square root of 2, okay, and so on. So you see, it makes perfect sense, okay. It makes perfect sense that we are actually seeing a square root of 2 in there. Okay, great. So fantastic. So we just have now stored the distance of all points, or the distance at which all points are from or with respect to the center, 0.0 or 0, 0. And but what is the problem here? Well, we have a little problem, and is this 0 here? Okay, because we're going to use these distances later on to normalize a certain result. Okay, and yeah, of course, if we have a 0 there, this means that we're going to be divided by 0. This kind of happened, right? So to avoid this problem, we're going to add a residual value here, so that we don't get a 0. Of course, it's going to be a very, very small number. But that is the function of it. So essentially avoiding dividing by 0. And what value? Well, it can be just this value. So 1 times 10 to the minus 12. Okay, for example, very small number. Okay, great. Now what can we do? Well, let's do the following. Let's again print this out for reference. Great. Okay, and now what we can do is just start say defining properly the glyph. Okay, because all what we've been doing is constructing, say, the grid itself, but we didn't start, say, coding the glyph. Okay, so let's do just that, and to start with, let's initialize glyphs. Okay, so here is where we're going to store all the glyph values, all the glyph representations. Okay, all the glyph patterns in this variable, this list. So for now, we just create an empty list. Okay, glyphs. Okay, great. As an empty list. Great. And now let's start our construction of the glyph. And to do that, we're going to create a loop. Okay, we're going to create a loop and what we're going to be looping through? Well, essentially, we're going to loop through the number of orientations, okay? Because we want a glyph per given orientation. We're going to create a glyph per or associated to an orientation, okay? So that's why we loop through all to create one for each. So let's do that. And well, in this case, it's going to be very simple because remember, we defined the number of orientations to be equal to 1. Okay, so we just expect to get actually one result. Yeah. Essentially, yeah. No, wait a second. Number of orientation here. Great. So let's start with this. And the first thing we need to do is to define the angle. Okay, so let's define the angle. And remember that we already faced this when we were defining the hard coding, or we were defining the weights for the DF filter, okay, for the DP, the directional projection filter. Yeah, we defined the orient, and we needed to introduce an angle. So here's the same, but with one key difference, okay, and that is that remember, here we are not taking into account the negative, say, direction. We're just taking the base number of orientations, which is equal to 9. Yeah, so indeed what we're going to have is the same kind of formula, but without these say 2 times multiplication. Yeah, so we're going to have np, so pi over the number of orientations. Okay, and we are going to multiply this by the the corresponding index, okay, to that orientation, right? Which is in this case just going to be 0, okay? All right, so now just to make things clear, more clean, let's print the following. So reference direction is going to be well, the corresponding index, and we have a corresponding angle to this index, of course, which we have just computed above. So it's going to be corresponding to, so the corresponding angle is going to be the following, and of course in radians. Yeah. Fantastic. So great. Okay, makes sense. So now what is next? Well, now we want to quantify. We want to quantify how well a specific gradient is aligning with the reference direction. Okay, and there's no better way to understand that than just visualizing, seeing the output tensor. Okay, so let me first write that down. Let me write down the formula that is going to give us the essentially the so how well is going to be aligned with the so the gradient, how well is going to be aligned with the reference direction or reference angle. Okay, and to do that we're gonna write a given vector with respect to its projections. Okay, so we're gonna write the following. We're gonna say vector written as projections. Okay, and to do that, well, we just need to write down the projections. So the projection of a vector, right? And well, this is just gonna be the following. So first of all, we need to take into account the horizontal value of the gradient, which is going to be, of course, the corresponding value in the u, so the u value, which corresponds to the x value in the two grids. So it's going to be u times the essentially the horizontal, the vertical projection. Okay, so it's going to be np sine. Okay, and the angle as given above. And same story with the say a vertical. Okay, so and angle. Okay, great. Now, well, can we leave it like that? Well, the best way to actually verify that is just printing out. Let's print out these results. Let's see what we get. Okay, so we simply get you see we get -1, 0, 1. Okay, so you can see that we got just the say yeah, okay. So let me actually verify something. What if we divide by the actual number of so the distances, so the tensor that stores all the distances. Okay. Yeah, indeed. So what I did just now is to divide by the number of distances of all the points. And why is that useful? Because that is going to just take into account the say given grid, and better say there's not going to be influence if a point is further away, say in an extreme of the grid, as compared to the a point that is nearby the 0, 0. And essentially it's just to normalize. We're just going to normalize the vector projections. Okay, so in order to normalize vector projections, we divide by n. All right, but yeah, now let's have a look at this result. All right, we just got these tensor right here. Okay, so the question is now, what does it mean, right? What does it mean? Well, let's analyze this. Let's analyze. Well, first of all, I like to first look at the simplest values, and well, we first get -1. Let's actually look at this -1. So if we see the point that this value corresponds to is 0 and -1, okay, 0 and -1, and so let's go to the graph here, 0 and -1, so it is in here, it is this point in here, okay, no, it is no, it's 0 -1, so it's this point right here, of course. Okay, so essentially we are looking at this say distance here. We're looking at this gradient here. Okay, 0, 1. Okay, is this value in here? So 0. So it's telling us that 0 -1, the value suited to it is -1. Okay. And same story with 0 and 1. Okay, so just narrow upper. Okay, and what happens with these 0, 0? Well, this is the reference value, so I understand that the distance, of course, between 0 and 0 basically is going to be 0. Okay, so why is then these positions, so -1, x is equal to -1, and y is equal to 0? Why is 0? Okay, why is 0? Well, let's have a look. So 0 and -1, we just saw in that the say tensor, that remember what that tensor is doing is quantifying how well is or say quantifying so how far away is our gradient from the reference, say from the reference angle. Okay, so first of all, what is the reference angle in our case? Well, let's have a look. Well, look at this. We're looking at the angle 0. Okay, so this means that the reference is going to be the following. The reference is this. The reference is the angle 0, so it's this line. Okay, is this line. Okay, because this line essentially has angle 0. Yeah, so what this is telling us is that if a given gradient, okay, is getting closer to this reference angle, so its value is going to decrease. Okay, this is exactly what it's telling us, because we just saw that for the 0.01, this line right here. Okay, we just saw that it's going to be 0. Okay, and if we actually verify the symmetric, the symmetric point, this 1 and 0, we should also get 0. Okay, so let's see. So 0, 1, 0, I mean 1, 0, remember that is the 0.10, so x1, and what is the 1, 0? 1, 0 is this, you see, 1, 0, and indeed we get 0 for that position as expected. So remember, if we are located in the reference line, we're going to get a 0 for these vector projections tensor. All right, while if we are outside the reference line, well, we're going to get a value that is non-zero. And what are the, say, values that are say bounding this study? So are going to be 1 and minus 1. 1 corresponds to 0 and 1. Well, 0 and 1 is of course the arrow that goes up, so will be this. Okay, so of course if we are in this position, if we're in this position, this is going to say be understood as being say the farthest away from the reference. Why? Because the angle is 90. The angle is 90. While if we are located in, say, the minus 1 1, minus 1 1, which is going to be see, minus 1 and 1, we're going to get 0.7. Okay, so we're going to have a value that is less than 1, and that is because that specific grid point is closer to the reference line, because the angle that corresponds to that is less than say 90. That is the 1. Okay, so that's the message. The message is that for these vector projections tensor, we're going to get the values associated to points. We're going to get that the greatest values, okay, are going to be those that correspond to gradients which have angles that are, say, maximum, okay, in the study. So in this case 90, and well, of course the opposite, minus 90. Okay, and you can actually see that 0.7 is the inverse of square root of 2. So you can guess that you're going to get the inverse of the say value of the distance. Okay. All right. So that is what we can understand from vector projections. But let's continue. Let's continue with the definition of a glyph. Because now, actually, what is useful to do here is to introduce a string. So say we can say quantification of alignment. Quantification of alignment. Okay. What's going on here? The other, yeah, okay. Okay, there we go. We have there the first, say, quantification of alignment. Yeah, let's call it like that for now. Okay, so what is next? So next is to introduce the glyph formula. Okay, the glyph formula, because right now what we just did was to essentially compute a vector using its projections. Okay, just taking the projections of the vector and normalize it. Yeah, but now let's introduce the actual glyph. So glyph, and that is going to be the following. So this glyph is going to be an exponential, and more specifically a decaying one. So we're going to introduce an exponential decay. Okay, we're going to introduce that, and we're going to take the absolute value of the vector projections and we're just going to scale it within a scalar. Okay, just randomly 15. Okay, there's no specific reason for that, just scaling it. All right, fantastic. So now we just have the glyph. Let's visualize it, because actually the best way to understand it is by looking at the output here. Let's actually print this out. Okay. Fantastic. So we can see something happening here. Okay. First of all, we now get ones where we had zeros. Okay, that is a significant change. There's a very significant change. So let me actually here also string. So glyph okay, let's see. Great. So first of all, we can see that the points that are aligned with the reference angle now are the ones that are maximum. Okay, and on the contrary, the points that, for instance, the ones that were maximum before, the ones that were, say, the farthest away from our reference, now are the smallest. You can see that now are the smallest values. So what this exponential decay did was to actually reverse the quantification of alignment. So essentially now what we need to understand is that the farther than gradient is from the reference, okay, the the greatest, so the smallest, sorry, the smallest value we're going to get, right? Because remember, this one corresponded to this point. So corresponding to the x is equal to 0, y is equal to 1. So the positive in here, this row in here, okay, corresponding to this row, this vertical row, and this is 90 degrees, right? So now, oops, nope, not this. So now, what we got is that we now have that the value is going to be the smallest. Okay, so so if the angle is greatest with respect to the reference angle, the associated quantity, okay, in the glyph tensor is going to be the smallest. Okay, that is the key. And also the key is that now the points that are aligned with the reference line are going to be the maximum. Okay, it's going to be 1, 1, 1, and outside this maximum, the greatest values are going to be those, as stressed, that have associated greater angle. Okay, with respect to the reference. Great. That is the message right there. That is the message. Okay, so now what should we do now? Okay, what should we do? Well, we continue now because we just introduced the glyph definition. But now what we want to do is to filter certain results. What do I mean by that? Well, let's have a look. So now what we're going to do is the following. I'm going to say if the dimension is equal to 1, okay, so exactly, so the dimension is going to be equal to 1. I'm going to state if the following is true: if the angle is going to be less than p over 4, okay, that is an angle that is between 0 and say 45 degrees, yeah, okay, over 4, or there's another possibility, that is that the angle is greater than 3 times pi over 4. So greater than 3 times pi over 4, okay, or less than pi, say, over 4, okay, so less than, in this case, say 90, so 90, no, 45 degrees, okay. Okay, in that case we're going to set dimension is equal to 1, and if that's not the case, then we're going to set it equal to 0, right? And no worries, because the best way to understand what this is doing is just to visualize the tensor output, okay? So let's just do that. So actually I'm going to print the following. I'm going to print okay, I'm going to do, so the maximum, okay, yeah, maximum column values on glyph are going to be the following. So I'm going to take the glyph, I'm going to put here, okay, glyph dot max I'm going to say dimension equals the dimension that we set above, and we're going to keep the dimension as it is here. Okay, and now we select 0. Okay, no worries, because I'm going to go through all this next. Okay, and now let's close this and set here space. Okay, but yeah, let's have a look at this. All right, so what is going on here? What is going on? Okay, let's think about that. Well, what I just did was to take the maximum values in the dimension specified, okay, above, out of the glyph, right? So remember, the glyph is this tensor right here, right? So I selected the dimension is equal to 1, all right? I selected that. Why? Because in this case, our angle, right? Our angle is less than pi over 4, of course, is 0, right? So as I selected the dimension is equal to 1, well, I'm just going to set we're gonna be looking at the columns. Okay, so hence we're gonna take the maximum values of glyph with respect to the columns. Okay, and why it is 0? Well, because we have a 2D tensor. Yeah, we have a 2D tensor, and more specifically, actually, we can have a look at that. So just for a second, let me do this shape on glyph. Okay, so that we can understand why we're putting this 0 here. Okay, so we have exactly. So we have these say a tensor here, which right now this glyph tensor is gonna be just a 1D tensor. By the way, this is, right now as it is just a 1D tensor. Okay, and of course it is, because look at this, we just defined an exponential here. Okay, we just apply the exponential, so all the results of the exponential are going to be stored in, say, in 1D tensor, unless we specify otherwise. Yeah, and we, by the way, will change that. We'll change the shape of it later. Yeah, but let's go now to understand the 0. So because what happens if we don't place a 0 here? What's going to happen? Let's see. Look, the output is a bit strange. The output is a bit strange because it's saying it's returning the type and values indices. So kind of it's not say returning just the values, the output values that we want. Okay, so I understand this as, look, we have a 1D, and I want to look at the elements within that 1D tensor. So if we want to do that, well, we will need to place, we need to specify that we want to look into that tensor. That's how I understand this. So that's why we need a 0, and in that case we indeed get the maximum values of the glyph tensor. Okay, great. So, but before that, let's put here and then. Fantastic, great. So now we have extracted the maximum values of the columns of glyph. Okay, and of course, as we explained, these values are going to be, well, let's go back to visualizing glyph explicitly. Of course, are going to be these values, right, in the second column. Great. Fantastic. So, let me think. Let me think 1 second. Because 1 second now. So why? Oh yeah, sorry. I mean, of course, this is not a 1D tensor. My bad. This is a 2D tensor, of course. This makes more sense. So you see, now we have, this is a 2D tensor, because I forgot. I was taking shape. Of course, this is a 2D tensor, which has 3 rows, 3 columns, right? And if we just visualize it, right, we're gonna have yeah, you see we have a 2D tensor with these 3x3 structure. So this 0 is telling, look, I want to get into these structures, so forget about this external dimension, and I just want to get in the tensor. That is why we place a 0. That makes more sense. Okay. Okay, so going back, now we just have these maximum values, and now what we want to do is to make a comparison. Okay, we're going to make a comparison, and a comparison between what? Well, we're going to redefine glyph. Well, not really defining, but we're just setting it to new values, right? New values of what? So we're going to make a comparison between the values of glyph as they are right now. Glyph. We're gonna see if they are the same, or what are the values that say align with the essentially these maximum values. Okay, we want to do that now. We want to redefine the glyph in that way. All right, well, let's do that. Okay. Let's see what we got. Of course, we need to print this. We should get bool types because we're comparing here. Great, exactly. That's what we're getting. So what we are doing in here is just saying, look, if we just set to true the values that are maximum and false the rest. Okay, just that's essentially what we're doing. Okay, and we're doing this to say make the following computations or the following operations easier, as we'll see. Okay, fantastic. So now let's actually put here a space and let's continue now. And what we're going to do now is to apply apply a mask. Okay, what do I mean by that? So we're going to apply a mask to keep the glyphs within the unit circle. Okay, why are we doing this? Why do we want to keep the glyphs within the unit circle? Well, because this is going to ensure that the glyph only focuses on the say relevant points, okay, inside the circle, inside the circle, right? And also because our HOG net, okay, is going to be based on circular symmetry. Okay, so just to apply or stick to this say rule of keeping just the information that is within the unit circle, we're going to apply this mask. So apply mask to keep glyphs within the unit circle. Okay, great. And how do we do that? Well, we just take glyph and apply it to n-1. N-1 here. Well, that is equal to. So essentially, what this is doing is just keeping the values that are within the unit circle. Okay. Actually, let's visualize that now. So let's visualize that. Okay, you see, we only kept the 0, 0 value. So that is the inner information, the information that lies within the unit circle. So that is the only information we're keeping for our glyph, essentially. Okay, great. But now, again, we did this because applying this operation is much quicker with say bools. Okay, with bool say characters or types. Now what we want to do is to actually get back say floats. Okay, so to do that we just simply convert the bool to float again. Yeah, so to do that we simply do the following. So print, we want to convert bool to float. Okay, and to do that, well, have a glyph here and like that. Let's see. Well, wait a second, because we need to convert this, of course. So wait, dot to, and we want to convert it to the type of float. So that is torch dot float. That, by the way, by default is going to give us a 32. So there's no need to extend this to 32. So let's have a look. Great. You see, now we get we get floats out of the bool types that we got prior. Okay, great. And now what is, say, the next step? Well, the next step is to reshape our tensor, okay? Because right now we have a 2D tensor. And remember that we have been working all the time, because again, what is really a glyph? Okay, so with glyph, we're just simply doing the same kind of, say, problem solving that we did with the previous gradients. That is, we first computed a way to hard code our weights, and then we went to our layer and replaced the PyTorch weights with the hard-coded weights. So here we are again doing something similar. Okay, we are first of all getting the hard-coded weights, okay, which are going to be the glyphs, and once we have that, we're gonna introduce a new layer, okay, that, by the way, we're gonna call render. And once we do that, we're gonna do the same process, so we're gonna replace them. Okay, great. But before that, we need to finalize. We need to finish with the glyph computation. Okay, because the glyph is going to be like completely analogous to computing, to hard coding the weights, okay, of our layer. All right, fantastic. So we just converted back to floats, and what do we do now? What do we do now? Well, what we need to do now is to reshape our glyphs, tensor, okay? But remember, we initialized a list here, empty list, glyphs. So what we can do is to start from there. So glyphs, and we're gonna append, okay? We're gonna append our values to that list. And what are we going to append? Well, what we're going to append is essentially the tensor that we got. Remember, because this is just one iteration. Remember, because we're just setting it equal to 0, right? To 1. So it's just one output, but the same applies to 9 when we apply the actual loop, so the actual HOG method of the HOG class. Okay, so glyphs append, and here what we are going to do is to append the glyph. So glyph, and and there are two alternate. So there are two options here. So either we do it the usual way. So essentially we take glyph and reshape it. We can reshape it to we want 4 dimensions, right? So first, second, and the rest is going to be kept the same. Okay, this is one option. And another option is to use slicing. Okay, to just use slicing. So just to change, right? Let's do it by using slicing, okay? Just to introduce a new method, right? But I'm going to put here alternative. And I think that this method only works when you have a square, square matrix, square tensor matrix, in our case in a 3x3. Okay, 3x3. So it's only going to work if we start from a square matrix, which in our case is going to be almost always almost always the case, actually. So yeah, in this case, definitely you can apply this reshape method too. Okay, but let's do that here. It's going to be here glyph dot reshape, and glyph is going to be dot no, not dot, we're slicing, so it's going to be none here, then another none, so all the new dimensions have none, and then we keep the information for rows and columns. Okay, great. And we just say appended the glyph gradient, or the glyph weights, you could call it, and to the glyphs list. So what is next? So now, well, what is next is to visualize what we got so far. So what we got is the following. So we got the following: print and the glyphs. It's always good to visualize, absolutely, to have a look, to have print statements in your loop when you understand it. So what's happening here? You see, okay. All right. Because I wonder why we got again, why we got again the I think I got it. So the problem is that we didn't store this in a variable. So this means that when you say apply these append, you are doing it to the previous one, you're doing to this one, which is still a bool. So you need to actually, instead of doing this, we need to define it above. So we need to do the following. We need to do a glyph. We need to do here, and this needs to be equal to this, and here is going to be glyph. Great. And now I should, now we should get exactly, you see, now we got the float values. Indeed, that's what we want. Great. Well, and beyond that, see how now we get a 4D tensor, right? Which is exactly what we want. Fantastic. But are we done with this? Not yet. There's a small thing we need to do still, and that is going to be concatenating this result. What do I mean by that? Well, look at this. Now we have a list. We have a list that stores a tensor with 4D. So we have a list that stores a 4D tensor, but we don't want that. We want a tensor that is 4D. That's all. We want to say get rid of this. You could call it less. All right. And how do we do that? So basically by concatenating. All right. So how do we do that? So let's understand how to concatenate, and to do that, I think it was torch.cat pytorch. Fantastic. So yeah, it is this. Okay, so concatenates the given sequence of tensors in the given dimension. Okay, here we have the example. Fantastic. So you can see how, yeah, we can apply this. We can use this. So we actually, I prefer just to do it myself. I think that's the best way. I recommend all to do the same. Just when you're learning, just code it out. So understanding concatenation. So torch.cat, right? So how do we do this? So essentially, what we can do is, okay, let's define a random tensor. And like that, and we have here, great, and let's say 2 by 2, right, for example. Let's visualize that. You see a 2 by 2 tensor, 2 rows, 2 columns, and let's actually print this for reference later. Great. What about, yeah, let's just play around. So what about if we apply concatenation to this random tensor, Okay. Well, let's have a look at the documentation and what does this say? Let's have a look. So on the tensor, okay, you see we have a look, and yeah, essentially this is indicating in what direction you want the concatenation. You want it in the rows or you want it in the columns. Okay, so say we want it in the rows. Great. So what's going to happen here? Let's see. Oh, error received. You see it's saying I was expecting a tuple of tensors. Okay, so of course what happens, do you think if I just put this in parentheses, it's going to work? So of course not, because PyTorch doesn't understand this as a tuple. If you want to specify this as a tuple, you need to put here a comma. Now it's going to work exactly, and you get the concatenation of the values. Okay, but let's see. Actually, let's do something. Let's yeah, because it might be confusing if I don't put here a space or even say original. Let's put here original. First string original tensor, original tensor, and here like that. Great. And nope, like that. Fantastic. So here, let's put here space. Great. So you can see nothing happened, right? Nothing, absolutely nothing happened to our tensor. Why? Because we, of course, this is a tuple, but not really, because there's no other element, right? So actually here there's something. You see exactly. So you can also run it with a 1D empty tensor with size number comma nothing, right? So if you just do that, nothing's going to happen. Okay, so if you actually want to concatenate, you need to place here the tensor that you want to concatenate your original tensor with. In this case, let's say we want to concatenate the tensor with itself with respect to the rows. Let's do that. Fantastic. So you see how now we concatenated our original tensor with itself. Okay, that is fantastic. So now it's clear. Just for fun, what happens if instead of 0 we place 1? Okay, so of course now instead of concatenating with respect to the rows, we just concatenated with respect to the columns as expected. Okay, great. So now we understand how concatenation works. So now let's actually apply it to our problem. Okay, fantastic. So let's see how it works. So essentially, yeah, so essentially what we need to do is just, well, we're actually done with this list because this is the end result. We have a tensor stored in a list, but we don't want that. We just want a 4D tensor. So to do that, we need to say, okay, so glyphs is going to be redefined. Glyphs is going to be equal to just concatenating the original, so the glyphs, the original tensor with respect to the rows. Okay, this is going to give us just the exactly. This is going to give us, you see, a 4D tensor as we wanted. Fantastic. So that is the definition of glyphs. Okay, we just got it. That is the, say, hard coding of the weights of a particular layer. What layer? The rendering layer, which we're gonna define next. Okay, let's do that. So let's here write the following. So 3.8.1 render layer. Okay, so let's first have a talk about this. So what is the aim of this layer? Well, it is to render the glyphs into a higher resolution image. Okay, so this is important. Let's write that. So the purpose of this layer, of this render layer, is to render the glyphs, into a higher resolution image. Okay, and to do that, we are not going to use the conventional com2d that we've been using so far for all the previous, say, layers. Okay, now we're going to use a different one. We're going to use so-called conv transpose 2D. Okay, so essentially, let's have a look at, well, let's mark this down. What is that, right? So conv transpose 2D PyTorch. So essentially, this is telling us, look, it's going to apply a 2D transpose convolution operator over an input image composed of several input planes. So look, and it looks very, very similar to com2d. Actually, all the inputs are essentially the same, right? So what is the difference? There's just one main difference, okay? And it's the following. So let's actually write that down. So we use conv transpose 2d instead of conv2d, because well, the former, we could say, is going to upsample. So because the conv transpose 2d is going to upsample, and what do I mean by that? So essentially, when I say upsample, I mean that conv transpose 2d is going to increase the spatial resolution. Okay, so increases the spatial resolution. Increases the spatial resolution. Okay, that is the height and the width, right? Of the output image with respect to the input. So this is the key difference. This conv transpose 2D is actually augmenting, is actually amplifying the input image, okay, and basically having as an output image one that is bigger, yeah, than the input. This is the reverse behavior that we observe in com2d. Com2d, normal as usual, observe is that it reduces the input image. So that is the main difference, right? That is the main difference. Well, either reduces it or keeps it the same if we add padding, right? Remember, we discussed about this. So, but conv transpose 2D, actually the goal of it is to augment, like amplify the input image, all right? And the question is, okay, why do we want to do this? Okay, this is because we want to map the glyphs, okay, into larger, high resolution images. We said in here. So when you're rendering, what you're doing is to map those glyphs into a higher resolution image. That normally implies, of course, a bigger image, okay, as an output. So that is why we use this conv transpose 2D instead of the usual conv 2D. All right. So let's actually code it out. Fantastic. So render, we're going to call the layer render, and we're going to have conv transpose 2D. All right. And the inputs are going to be very, very similar. Actually, are the same than conv 2D, right? So what are going to be our input channels? Well, our input channels are the number of orientations, because remember, we're going to have one glyph per orientation. All right, so that is why we're going to have as many say input gradients as orientations we have. Great. As an output, we're just going to have one output channel as a result, okay, which of course is going to be bigger than the original image. So what we're doing here is to actually map the already constructed glyphs. All right, remember this glyph is a visual pattern, and remember there's one per orientation, so we're just storing those into a high resolution image, so a bigger image, right? Well, a single one, right? And what is going to be our kernel? Our kernel is going to be actually the size of the, say, a glyph that we say set above, in this case 3. All right, so by 3 kernel in this case. Remember that in the original going to be 21, so a huge kernel. And the stride is going to be actually GS2. So why are we setting the stride equal to GS? Well, the stride, remember, determines the spacing between, in this case, glyphs. So it's going to determine how much space there's between glyphs. All right. So by setting it to GS, each glyph is going to be placed exactly in its corresponding grid cell. Okay. This ensuring, or this results in no overlap whatsoever. Okay. That is why we are setting stride equal to GS. Right. Fantastic. So again, the bias we set it false, as we've been doing for all layers we've defined so far. Okay, right. So now, well, what is next? As always, remember, I mean, if you see, it really has a mechanism that repeats over and over again. All we're doing is first hard coding the weights, and next we define the layer using PyTorch built-in classes. Of course, we've been using com2d, and now we introduce the com transpose. No. And essentially after that, what we do is to replace the PyTorch weights with our own. All the time like that, right? It's all the time like that. Fantastic. So now it's time to do just that. We need to, as always, extract. We need to extract the weight. So as always, we extract the PyTorch weights, and let's have a look. Let's have a look at those. So render the data. Let's have a look. Okay, so it is a 4D, and well, I would like to, well, we just visualize the values. Okay. Actually, for the sake of clarity, actually, let's print also the values. So values, and I will also print the shape. Let's do it. Okay, so 3 by 3, and we have these values. Fantastic. And remember, now we need to compare with glyphs. We need to compare with glyphs. So let's do just that. So print, and we need to print glyphs. Great. You see. Yeah, how they differ. Of course, we just got 1 in our case on this analysis. We ended up with just 1 as kept, right? And we want to replace the original PyTorch weights by our own. Yeah. So let's do that. But first question is, can we do that? Of course, you can see that you can already guess. By seeing that we can do it because they have the same shape, but just to actually sit in the L screen, actually what we can do is the following. We can actually do this So we can do weight.data.shape, and is this equal to the shape of the glyphs? That's a question. Okay, let's see. Shape is true. Fantastic. So as it's true, then we can definitely write down the following formula. So we can just equalize the PyTorch, so we can replace the PyTorch render weights by our own. So glyphs. Okay, fantastic, fantastic. So, and as you can see, we could very easily say automatize this process, because we're always doing the same. We're just computing the say the weights, then getting the layer and replacing the layer weights by our own, right? But yeah, that is all I wanted to discuss today. I hope it was useful, and I am willing to see you very soon.